Hey everyone, my name is Ian, and today I'll be presenting HOLMES, which is an efficient distribution testing framework for secure collaborative learning. This is a joint work with Katerina, Weikeng, Murat, and Raluca. So machine learning is everywhere. Almost every organization nowadays can be seen training their own models. It's also well known that having more data leads to better trained models. In this case, multiple organizations can collude or combine their data sets in order to train a joint model, which will lead to better accuracy than training individual models. In this framework, we can introduce the privacy constraint. Specifically, banks may want to hide the information of their customers because of legal reasons. More formally, in this scenario, we can have that parties are not allowed to share their data with any other party. Another idea in this setup is we have the security guarantee. Specifically, we use malicious security with a dishonest majority. This says that up to n-1 out of n parties can deviate arbitrarily from the protocol. This is essentially to prevent any single party from not adhering to the rules of the protocol, but aborting the protocol in case if any party deviates. So one issue with having this privacy constraint is that parties can input corrupted data sets, but due to a privacy constraint, there's no way for any other party to check whether this input is correct or whether the data set itself is corrupted. So how exactly can we check that the data set is corrupted without looking at each party's individual data itself? The first attempt we can do this is with range checks. Specifically, range checks enforce the range of values that each input can take. And this is previously the only state-of-the-art technique against malicious input checking. In our past example with the banks, we can have a customer and filter out any inputs such that the age has to be greater than or equal to 0, or the age also has to be less than 120, which is the age of the oldest person in the world. Previous works that have implemented range checks for input checking include bulletproofs, Prio, and Prio Plus. However, are range checks enough? As we could see in the last example, all we did was filter out the negative age, but we can introduce something else known as distribution testing, which will check the properties of the distribution of the underlying data. And by introducing a distribution test known as the mean check, we can check whether the mean of the distribution is approximately equal to 50. And we get a distribution very close to what we want in the end, which is approximately a bell-shaped curve. So as we can see in this example, combining distribution testing along with range checks is much more powerful than just range checks for checking the input. So this is our work in HOLMES. We check malicious input using distribution testing. And we also, like I previously mentioned, operate in the highest level of security, which is malicious security with a dishonest majority. And as we see, HOLMES will perform distribution testing much faster than the baselines, as we describe later. So distribution testing has many real-life world cases. One case is pragmatic clinical trials, in which we can compare the NIH Collaboratory recommends hospitals comparing distributions of data sets to detect data discrepancies. Another use case is group fairness, which says that if you have a biased data set, then the trained model on that data set will also be biased. And the way that you can check and detect and remove these biases is through distribution testing. And third, we have data quality. This says that the model of the joint data set of all the data sets combined together, as long as these data sets are of good quality, which we can ensure with distribution testing, is going to be of much greater quality or accuracy than individual models trained on individual data sets. So one issue with distribution testing is that it cannot detect input poisoning attacks. By input poisoning attacks, I mean by smaller perturbations to inputs that cannot be detected by distribution testing and range checks. These detect larger, medium to larger perturbations to inputs. So we leave this as an open question as to how to detect input poisoning attacks. However, we note that input poisoning attacks are ineffective in certain cases, such as federated learning. So continuing on with moving forward with the presentation, I'll describe the framework behind how we build HOLMES. So first, we use zero-knowledge proofs for fast distribution testing. Zero knowledge proofs allow us to offload and verify the computation of local data sets, whereas in the original case, we would perform all the computations online using multi-party computation. And offloading and performing these local computations offline is going to be a lot more efficient than performing all the computation online. But this is a relatively straightforward technique, so we refer to the paper for more details. Next, we show, in this presentation, we'll go more into how we design efficient multidimensional testing. And as we can see, this is much, much faster than the strawman, which uses a naive when hot encoding approach. And we'll go through the experimental evaluation and show that Holmes is much faster at distribution testing than both naive approaches. So one of the most powerful distribution tests available is known as the histogram check. You can check whether the distribution of the data set is going to be close or closely related to the distribution, to a public distribution that's widely available. In our bank example, we can check whether the distribution of the age data set is going to be similar to just a public age distribution available freely on the internet. And the way we can do this is Pearson's chi-square test. Specifically, Pearson's chi-square test checks whether the distance, the L2 distance in between a party's or a bank's data set distribution and the public distribution it's being compared to is small. But what if we want to compare with input data that is more than just age? Let's say we have a customer object that contains an age and an income, or we have an age column and an income column and a gender column. How exactly do we compare a histogram of a single input entry of that instance? And one first but incorrect approach is by splitting up each individual attribute or each individual column and performing separate histogram checks for each individual attribute. So in this bank example, we can just extract the age column and we can compare it with the public age distribution. And we can also just extract the income column and compare that with the public income distribution. And as we can see, these distributions are close enough so the Pearson's chi-square test should pass as is. But if we perform it in the correct way, which is we join the age and we join the income column, if we essentially take the entire input entry and get all combinations of age and income, then checking the histograms for these individual attributes will both pass, but this test where we join the columns together will not pass. And one huge issue with this is, of course, the number of histogram bins will grow exponentially to the number of attributes or the number of columns that you want to join. Pearson's chi-square test will be extremely expensive in this case, and we need to think of something new that's a lot more efficient. And our solution is using a sketching approach with something known as the Johnson-Lindenstrauss lemma. Essentially, at a very high level, what we do is we take this histogram with an exponential number of columns and we project it into a histogram with a constant number of columns as seen on the right. The way that we can randomly project this into a constant number of columns is using the Johnson-Lindenstrauss lemma, which says that the norm of this histogram vector is going to be preserved if we multiply some pseudo-random matrix with a constant number of rows by this histogram vector. And this matrix vector multiplication is very efficient and can be done in a constant number of operations. The only issue with this is that our approach only works when comparing a secret or a party's dataset distribution to a public distribution. But if you want to compare two parties' secret datasets with each other, this approach will not work, and we leave it as an open question as to how to solve this. So moving on to our experiment evaluation, we use Quicksilver for a zero-knowledge protocol and ScaleMama for MPC, multi-party computation protocol. We use AWS instances where each individual instance represents a different party in the protocol, or let's say a different bank that has its own unique data set. And we vary the number of parties, the size of the input, and we also vary the data set type. So we can have a bank marketing data set testing workflow versus an ad auctioning data set testing workflow. And we see that Holmes, with using this zero knowledge proof approach to offload the local computation, will provide a 10 times speed up, but the sketching approach with the Johnson-Lindenstrauss lemma will produce a 10,000 times speed up for multidimensional tests. As we can see right here, by just using zero-knowledge proofs to offload the computation, we see that not only the overhead grows much slower by offloading a lot of the local computation, but also at an input size of 200,000 entries, we get a 10 times speed up. And also, moving on to the multidimensional distribution histogram check, remember as we project a histogram with an exponential number of columns into a histogram with a constant number of columns, the overhead also remains relatively constant as we increase the number of attributes. Whereas in this log plot, we see that as we increase the number of attributes for the naive approach without our sketching approach, since the number of histogram bins grows exponentially with the number of attributes or the number of columns, then similarly the overhead grows exponentially. And just at 5 attributes or just at 5 columns or 5 different attributes per input entry, we have a 10,000 times speed up using this sketching approach. So overall, we present HOLMES. This is an efficient framework for distribution testing, and as we can see, is also a lot more efficient than using the baseline generic MPC approach with using one-hot encoding vectors instead of a sketching approach. With using zero-knowledge proofs to offload a lot of the computation, we see a 10 times speed up. And by using the sketching approach with the Johnson-Lindenstrauss lemma to sketch the exponential number of columns to a constant number of columns, while closely preserving the norm, we see a 10,000 times speed up. And check out the ePrint paper for more details. Thank you.